Today I'm going to talk about, let me just put a pointer, laser pointer, this topic. And then, so when I was asked to give this lecture, so I understood that this is more about stimulating discussion. So I'm not going to talk about anything new, but some of the things I've learned in the literature, and then me and mostly my long-term colleague, Garth Vanderkamp, thought about it, about this groundwater flow systems, which of course was uh, originated by our dear friend Joseph Toth back in the early 1960s. So at the time, Joseph was walking in the Canadian prairies, similar to this picture here. You have this, little valley, so that adds a topography to the flow system. Um, but then what we don't see in this photo is the complex heterogeneity of geology underneath, and particularly the change in hydraulic conductivity by several orders of magnitude, even within the top, 20, 25 meters. So that has important effects on groundwater flow system. So I'm going to talk about that using a Canadian example. So just a historic perspective a bit. So you might have seen this picture in his very informative and interesting paper. This is his autobiography published in Groundwater. Um, so Joseph, of course, came from Hungary, but he settled in Alberta in late 1950s. So he was hired by Bob Verbolden, also Peter Maibum, who is also in this picture. So Joseph was a geophysicist by training, but for some twists and turns, he had to work on hydrogeology. So he thought he would learn about hydrogeology by this big paper by M.K. Hubbard. So it's a theory of groundwater flow. So what Hubbard did in this paper is to borrow the potential theory to explain the pattern of flow. So Joseph, of course, saw this and studied it, and then he thought he would apply it to the field setting, but then he went out, and what he saw was this. So there's a dry creek, so there's no, the point sink of water where all the groundwater is converging to the creek bed. So then he, thought about it long and hard, and then according to Joseph, there was an epiphany one day when Peter and Joseph was camping during the field work. So the thought was that, well, so this model of Herbert was based on theory and mostly conceptual. He must have borrowed it from potential theory involving a point sink, but indeed, the actual hydrogeology involves boundary conditions. So he thought, he would impose more realistic boundary conditions, not just a point sink, and then solve differential equations in mathematically rigorous manner. And then what he came up with something that looks like this using contemporary groundwater simulation. So instead of point sink, there is a zone of discharge. So there will be evapotranspiration loss from the ground and maybe a little bit of flow into the creek bed. And then he put forward this idea even further by including more complex topography. And then the end result is all we know. So it's a new paradigm of groundwater flow system. And then this was immortalized by the textbook published by Fries and Cherry back in 1979. So I was born in 1963. So of course, I didn't really read Joseph's original paper. when it was published. But I learned about this theory through this textbook. Chapter 6, in my opinion, is the best chapter in this textbook. And then, so reading chapter 6 of this textbook was one of the reasons why I came to Canada to study my PhD at the University of Waterloo. So many people have many different experiences about this diagram. And of course, this groundwater flow system is the reason why we're gathering together here online. So just look at this concept a bit more using the picture from the original paper. So you have this nested flow system or hierarchical flow system. So you have local flow system, intermediate flow system, and regional groundwater flow system. And then it it is appealing and it makes sense to a lot of us who have studied the groundwater. But when you look at this diagram carefully, this is the discharge areas. So there's many discharge areas corresponding to different flow system. So when you look at it carefully though, so you note that scale.
Back in a minute.
So the horizontal scale is 6 kilometers, which is some distance I can run in about half an hour or walk in an hour and a half. So it's a walking distance, basically. It's a small watershed. And then the flow system has a depth of 3 kilometers. So that's a depth of oil and gas wells drilled around here. So there seems to be a bit of discrepancy in the scale, from our general experience. And also, because Yojev had to use paper and a pencil to solve the differential equations, he had no choice but to use a uniform material. So what this diagram is saying is that geology is completely homogeneous, uniform, down to 3 kilometers. So that seems strange to me and also to many hydrogeologists. And then this was noted as early as 1962. So the Research Council of Canada organized a number of hydrological symposium back in those days, 1960s and 70s. So there was a symposium on groundwater hosted at the University of Alberta Calgary campus, which is University of Calgary now. So it became a university in 1966. So this year we're actually celebrating 60th anniversary of the University of Calgary. Now, back in those days, symposium or symposia are actually symposia where people would gather together and discuss ideas. So the presenters, there are only a small number of presenters, they actually had to submit a written paper to the organizers months before the symposium. And then all the participants would read the papers and then have their own thoughts before they showed up at the actual symposium. So discussion was a very important part of the symposium. So this symposium took place in the building right next to where I am sitting now, just a minute walk from my office. So the Yojev presented his paper on the nested flow system. So the journal paper was published in 1963, but then actually presentation was already done in 1962. So after Yojev's presentation, Peter, at this point, Peter had already moved from Alberta Research Council to Geological Survey of Canada. So Peter stood up and then made a comment. Joseph's assumption that the medium of groundwater flow in small drainage basins may be treated as homogeneous is contrary to all geological observations in Western Canada. Contrary to all geological observations. So this must have stirred some heated discussion, but of course I wasn't there. So this was discussed even at that time, but largely ignored since then. So instead, Maibum gave his presentation in which he presented what we call the prairie profile, which seemed to match with the field observations of hydrogeology in the Canadian prairies. By the way, this prairie profile is also in the chapter 6 of Freeze and Cherry. So Josef's idea was that we can do a mathematically rigorous treatment of groundwater flow system using differential equations, which greatly helped fundamental understanding of hydrogeology, which would benefit even today. But Maibum's idea was that we need to take a geological realistic approach, which is consistent with the field observation. So the question is, can these two ideas, both are valid, can they be reconciled? So then this prompted the development of a numerical groundwater flow model by Alan Fries, who was working with Peter Maibum while he was conducting his PhD studies in California. And then, of course, that was the beginning of numerical groundwater flow modeling, which we all benefit today. So going back to this notion of geology not so uniform, here are some examples. This is for the glacial till, which covers most of the Canadian prairies, including the places where Josef had developed the groundwater flow system concept. So this is our own work. Garth and I measured lots of hydraulic conductivity in the till, and then noted exponential decay by several order of magnitude, 2, 4, 6 orders of magnitude indeed, within 25 meters of the ground surface. This was a more recent work by David Ferris, Grant Ferguson, and others at the University of Calgary, still noting the same trend. So this is for the unconsolidated sediments. And then Xiaowei Jiang did a lot of important work on this topic about 15, 20 years ago. So he compiled the measurement of the hydraulic conductivity and then made some mathematical models of that. This is based on Chris Neusel's data from Pierre Shale in United States. And then this is for granite based on the data from Stripa in Sweden. So this is just a few examples, but I know many more examples indicating exponential decay of hydraulic conductivity with depth by several orders of magnitude. So we need to admit that the geology is not uniform. So the decrease in hydraulic conductivity by order of magnitude is more of a rule rather than exception. So Xiaowei, of course, noted this earlier, and then he put that into a numerical groundwater flow model. So this was using a code called COMSOL physics. And then, so this is a case with uniform hydraulic conductivity. So you get the standard nested flow system. So these red lines indicate the pattern of flow. So you got local flow system, intermediate flow system, and a regional flow system. And then what we need to note is this magnitude of flow vectors. So the flow vector actually are larger near the surface, smaller at depths of a kilometer. But still, even at the kilometer, the flow vectors has still significant magnitude. And then they put this exponential decaying hydraulic conductivity. K naught is the surface value, and then K decreases exponentially as a function of depth. This is the decay coefficient. So in the first example, they used a value of 0.005. With this value, hydraulic conductivity at the bottom of this domain is 0.007, about 2 order of magnitude decreases, which is a pretty mild decrease. But even with this mild decrease, just by 2 orders of magnitude, flow vector is almost invisible here. So all the important things are happening within top few hundred meters. Now, so you increase the value of A. So now the hydraulic conductivity at the bottom is about 4 orders of magnitude smaller than the surface value at the bottom. So it's probably reasonable for the actual geology in many cases. So the red lines are still there, but it's still there because the model draws this equipotential line and streamline, but magnitude is only significant near the surface, maybe within the top 100 or so meters. So they demonstrated that this is a reality of the flow system. So we need to really focus on the part that flow is still very active. And then Xiaowei worked with Bayani Cardenas on another paper. This time they were going to focus on solute transport, but I'm showing the results for the flow part from this paper. So again, using the exponential decaying hydraulic conductivity. So this is a case with the constant hydraulic conductivity. So the color indicates the magnitude of flow, the Darcy flux divided by the value of hydraulic conductivity near the surface. So this is log scale. So it decreases from 10 to minus 2 to 10 to minus 20, which is almost negligible. So constant K, the flow is still somewhat relevant, even to the great depths. And then the hydraulic conductivity decreases to 0.05 of surface value at 1 kilometer here. So now the value near the bottom drops to 10 to minus 8. So this is basically negligible. And then going to even higher contrast, conductivity is 4 order of magnitude smaller at 1 kilometer. Then the only part that flow is still active is near the surface. So this is another demonstration that the exponential decay of hydraulic conductivity really focuses the flow in the local flow system. So from these and other studies, we can learn that important things in general, though there are some exceptions, but in general, important things all happen in local flow systems. So therefore, those are the flow system that we have to focus on for environmentally important problems. The effects of deep, long-range flow systems, kilometer deep and hundreds of kilometers long, are generally unimportant for environmental problems, except under some special settings, such as a well-developed karst system or extensive and continuous deep aquifer. So we're talking about things the general population might call the underground rivers. Unless we have those special settings, deep long-range flow systems are not important for environmental problems. So I'll just show you a Canadian example to underscore this point. So this is an example of prairie wetland hydrology. So this is a typical picture of prairie wetland. So prairie is a dry place, but we have lots of wetlands. So these are important ecologically because these wetlands have this nutrient, these aquatic invertebrates rich in protein and fat, and that feeds this migratory waterfowl that travel long way from Mexico and the southern United States to breed in Canadian prairies. So So just a bit about hydrological condition of the Canadian prairies, which is essentially the Canadian part of the northern prairie region, or sometimes people call it the prairie pothole region. So it's a dry place. The precipitation ranges generally from 300 to 500 millimeter per year, whereas the potential evaporation can exceed 700 millimeter per year. So there's a moisture deficit during the growing season. So summer runoff is very rare. And yet we have a cold winter, the temperature gone down to minus 30 degrees, and soil is frozen to a meter and a half. So very little runoff generation in summer, and then runoff is generated during the snow melt, which is happening in Calgary now. So I was out in the field site a couple of days ago, just see the snow melt, and the ground is still frozen. I can feel the frozen solid ground, yet the snow melt runoff is flowing over this frozen ground. And then this whole area was glaciated several times. So the last glaciation, Wisconsinian glaciation, left a thick pile of glacial sediments called till, which is generally rich in clay. So this is a picture I was drilling. I just stuck a knife in this till, and then the knife doesn't drop. It's so hard and tight. And then, so this is undulating landscape left by the glacier, and then has a lot of closed depressions. So that acts as closed hydrologic basins. So the topographic depressions. So these depressions collect all the snow melt runoff over the frozen ground. And then, so these depressions fill up with water in the spring, such as in this picture, and then gradually comes down because of evapotranspiration and loss to the underground sediments. So this highly seasonal pattern of water level in these ponds in depressions. So because these prairie wetlands are ecologically important, also hydrologically interesting. So there was an effort to study these wetlands by the Canadian Wildlife Service. So they set up this large area near Saskatoon in Saskatchewan, right here. And then so they studied the ecology and the hydrology of wetlands. So I'm just going to show you two examples of wetlands, 109 and 50. So 109 is smaller and has a seasonal pond. So the pond that will disappear every summer and then appear again in spring. And then it has a fresh water, low electrical conductivity. And S50 is more permanent and has a saline water, so high electrical conductivity due to the presence of salts. These are sulfate salts, not the sodium chloride. So this color coding is used throughout: blue for the seasonal and freshwater wetland, and red for more permanent and saline water wetland. So here is the pattern of water levels over the 1960s to 1990s. So this period, early to late 1990s, was when I was working on this with Garth on my PhD and a subsequent work. So as you can see, the seasonal pattern and the more of a permanent pattern. And it changed after that because we had a wet period. So all the wetlands in this study site became more wet, and even the seasonal wet pond became permanent pond in this wetland. And this is because we have this large interdecadal change in precipitation. So we have a wet period for 5-6 years, and then dry period follows. So deluge and drought. So this past 20 or so year was a big wet period followed by the drought period. So now this seasonal pond became seasonal in the last few years. So it's going back to the condition of 1970s and 1980s. So this, highly seasonal and also highly dependent on meteorological conditions. So I'll talk about that a bit later. Now, so because of the importance of these wetlands, there were studies done as early as 1960s by Canadian hydrologists. So this original study was actually done by Peter Maibum, who was working with Joseph Toth when the flow system concept was developed. So this is a famous wetland studied by Peter Maibum. So I was doing my PhD back in 90s with Garth. And then I thought I would have to pay a visit to this holy place of prairie wetland hydrology. So I took this picture in 1995. So, of course, Maibum was working on this wetland right when the flow system concept was developed by Joseph. And then, so there were a lot of influence of this, the ongoing discussion of groundwater flow system to the colleagues of Peter and others. So Al Lisi was a hydrogeologist working with Peter at Geological Survey of Canada. So he took the idea of the regional, the groundwater flow system and applied to this prairie wetland setting. So you have recharge area. So, the wetlands in recharge areas, which is topographically high position, would be called the recharge wetland. So these two. And then the ones in the topographic low areas, so discharge areas, are called discharge wetlands. So Lisi noted, so these wetlands have fresh water and these wetlands have saline water. So they seem to match with the pattern of flow. And there are some somewhat intermediate ones called the flow-through wetland. The water comes from one side and goes out to the other side. And note that these recharge-discharge pair were connected by either intermediate flow system or regional flow system, because geology is supposed to be homogeneous in the glacial till. So you'd have an important contribution of regional and the intermediate flow system. So this influenced thinking by ecologists. So the ecologists developed this concept of the wetland continuum to explain eco-hydrological diversity of prairie wetlands. So let's focus on this freshwater recharge wetland. So due to this large swing between wet decades and dry decades, so the condition of a wetland changes. Some years, the ponds are more permanent in the same location and less permanent in the same location. And then this is considered the time part of the space-time continuum. And then this is the space part. So the groundwater recharge and discharge connected by the regional flow system and the intermediate flow system governs the salinity of wetlands. So they support different ecosystem adapted to the freshwater environment and the saline water environment. And this is all based on the notion that groundwater flow provides input to this discharge wetland through the intermediate and regional flow system. But what they didn't consider, of course, is the fact that hydraulic conductivity drops by 5-6 orders of magnitude, even within top 20-30 meters. And what's important here is the transition from highly weathered and fractured till that has a secondary hydraulic conductivity, which is high enough to carry the active flow of groundwater. And below that, the till is so tight that there's basically no flow in this part deeper than 5 or 10 meters. So what we have in reality is, okay, we still have recharge, discharge wetlands, but the contribution of intermediate and regional flow is almost negligible for the water balance and then solute mass balance of these wetlands. So then how these discharge wetlands are getting water input, which make them more permanent and also more saline. So the answer was in surface water. So while we were working, Garth and I were working in this prairie wetlands in St. Denis study area, we know that sometimes we have overflow of water from one wetland to another. And then it terminates in this wetland 90, which is considered a terminal wetland in this system. And later on, we used a new technology called a LiDAR. Okay, LiDAR was then a brand new technology which allowed the generation of detailed digital elevation model. And we know that this area, which was our world at the time, was actually only a small part of the larger world. So this S90 was the terminal wetland of a gross drainage area as large as 8 kilometers squared. So water input to a lot of these discharge wetlands are by surface water driven by snowmelt runoff, not by groundwater. So this is the revised conceptual model. So we still have recharge wetlands in high position and the discharge wetlands in low position. And then all wetlands have a very active exchange of groundwater with the riparian zone. Because this part, which is saturated and have high saturated hydraulic conductivity, allows active flow of groundwater. But underneath, there is still gradient, there is a flow vector, but this flow vector is so small, on the order of a few millimeter per year or a few tens of millimeter per year. So not enough to affect the water balance of these wetlands. But this, a few millimeter per year is still important for the recharge of regional aquifers, which, farmers are pumping groundwater from. And also the fact that there is an upward gradient, not downward, okay? The flow vector doesn't have to be very large. As long as you have an upward gradient that prevents the downward flow, the salts that are brought into this discharge wetlands actually accumulate over thousands of years, and which develop these wetlands into the one with high salinity. So I have just demonstrated one example that the groundwater flow system, the understanding of groundwater based on the uniform geology had misled the development of incorrect model of eco-hydrology of these prairie wetlands. This actually resulted in some negative influence on the management policies and planning of these prairie wetlands. So what we should have done is to use more correct understanding of hydrogeology to develop the policy and management framework. So this is the final thoughts. So I'm going to use another example on mountain groundwater flow. So here is a picture of a prairie farm. So it will look like this now. So the snow has melted. It's almost all gone. And from the farm around here, you see the mountains. So you talk to the farmers, who rely on groundwater, and they say, well, our groundwater comes from snow melt in the mountains, because you can see the mountains there. And then this picture that there is a big flow system originating from the mountains coming to the prairies just kind of is appealing and also makes sense. But what we need to understand is that only the top few hundred meters, maybe 100 meters of the mountains have high enough hydraulic conductivity to allow meaningful amount of flow. So really, the all important things happen within the top 1 to 200 meters of the mountains. So we may have some thrust fault and fractured zones, but these are usually local and limited to the local influence. So for example, we have this famous Banff hot springs. That's driven by this one with those thrust faults, but those are unique. So by and large, all interesting things happen in the top few hundred meters. So what we need to do is to use that more realistic understanding of geology. Now we have numerical models, highly sophisticated ones, to develop the conceptual model and guiding those conceptual model to make the policy, the assist with policy decisions. So another way we can, so I just go back. So this is one way we can effectively use the groundwater flow system concept using more accurate geological information. The underlying concept is still a groundwater flow system. So another way we can use groundwater flow system concept is as an educational tool. Especially when it's combined with simple numerical models, we can demonstrate important concepts such as a nested flow system or the effects of a breaking slope on the pattern of groundwater flow, or even the effects of heterogeneity, geological heterogeneity on the groundwater flow system. But the one I use all the time, even when I'm not teaching, is a guide for the field reconnaissance. When I go to a field site the first time with no previous measurements, I just rely on this IAH-RGF's flow system concept and my own eyes to understand the boundary condition. And sometimes you identify the relationship between topography and the presence of groundwater-dependent plants. So when I was working on my master's thesis in Japan, this was many, many years ago, one of my supervisors told me, he was a friend of IAH-RGF and a great admirer of IAH-RGF. And he would tell me and all my fellow students, you guys, when you guys, walk around for field work, you guys always need to think about the boundary conditions. So that's how you understand hydrogeology in the field using IAH-RGF's concept. So finally, groundwater flow system concept is fundamental to hydrogeology, but we just need to acknowledge its limitations and use it effectively. So this is my final word. Thank you very much for your attention.